Hello everyone, I am Anandavalli. I welcome you all to Guidance Education channel. In this video, we are continuing Class 11 Chemistry, Chapter 4, Chemical Bonding and Molecular Structure. Under that, we are doing valence bond theory. We have discussed many concepts under that topic, and here we are continuing hybridization. In the previous video, we have already seen that hybridization is mixing up of near energy level orbitals of the valence shell of central atom to form hybrid orbitals of same energy level with distinct directional property. This concept of hybridization helps to explain shape, that is geometry of molecules. There are various orbitals like S, P, G, F, etc. These orbitals have their own properties like shape, number of orientation, energy levels, etc. Different shells have these orbitals. Valence shell alone is considered when we talk about hybridization. Our topic in this video is type of hybridization. Hybridization is classified on the basis of the orbitals taking part in this process, that is, the orbitals that mix up. As a result of mixing up, hybrid orbitals are formed. Number of hybrid orbitals will depend upon number of orbitals that take part in hybridization. Types of hybridization is a vast topic. It will be very difficult to understand it if we discuss all these types together. So in this video, we will restrict our discussion to one type of hybridization called sp hybridization. As I told earlier, type of hybridization depends upon the orbitals that are taking part in hybridization. So sp hybridization is a hybridization where the s orbital hybridize with p orbital. You already know the s orbital has spherical shape, whereas the p orbital is dumbbell shaped, that is with two lobes. The nucleus of the atom will be somewhere here and the electron goes round the nucleus in this pattern. S orbital has only one orientation, whereas the p orbital has three orientations. These three orientations are mutually perpendicular. One will be in the x direction, another orientation along the y-axis, and the third one along z direction. We will show these three directions as lines. This is the x orientation, this is the vertical y orientation, and you have the z orientation. X and y are perpendicular, y and z are perpendicular, x and z are perpendicular. So all the three are mutually perpendicular. The three orientations of the p orbital are called px, py and pz. This is p1, p2 and p3. If the s orbital hybridizes with one of the p orbitals, you remember all the p orbitals are degenerate, that is having same energy. So if the s orbital hybridizes with any one of the p orbital, it is simply called sp hybridization. If s orbital hybridizes with any two p orbitals, it is called sp2 hybridization. If all the three p orbitals hybridize with the s orbital, then it is called sp3 hybridization. For sp2 hybridization, there will be three hybrid orbitals, and for sp3 hybridization, there will be four hybrid orbitals. For sp hybridization, there will be two hybrid orbitals. So there is sp hybridization, sp2 hybridization and sp3 hybridization. The type of hybridization taking place in the central atom of the molecule will depend upon the number of orbitals that are required for bonding. I have already said that the orbitals have their own specific properties. So the hybrid orbitals will have a hybrid property, that is a certain percentage of S characteristic and a certain percentage of P characteristic. It depends upon the number of P orbitals hybridizing with the S orbital. In this video, we are discussing sp hybridization. Here, the two hybrid orbitals will have 50% S characteristic and 50% P characteristic. You can see from the diagram that the p orbital has two lobes which are equal. It is dumbbell shaped. Now let us see the nature of the hybrid orbital formed when the p orbital hybridizes with the s orbital. Look at the shape of the hybrid orbitals. One lobe is big and one lobe is small. In sp hybridization, two hybrid orbitals are formed. So I have shown here two of them. I have shown them oppositely placed only for saving some space. The electron in this orbital will move in this fashion around the nucleus. It is represented like that. And in your textbook, you will see, depending upon the wave function, one lobe is represented as positive and the other lobe is represented as negative. For convenience and for easiness of understanding, we may take that the positive lobe has more electron density. Now I will explain the concept of hybridization and bond formation using the example of beryllium chloride. Beryllium atomic number 4, chlorine atomic number 70. Let us first understand this structure. These 4 electrons are arranged as 1s2, 2s2, 2p, 0. There are no electrons in the p orbital. So all the 3 orientations are empty. This is the ground state of beryllium. When we represent the molecule, how do we represent it? Beryllium in the center and 2 chlorine atoms attached to the central beryllium atom. This is how we show this. So the angle here is 180 degrees. We have to explain how this bond is formed and how this 180 degrees is achieved. For that, let us take up chlorine atom. Chlorine atom, atomic number is 70. The orbital picture of chlorine in the ground state can be represented as neon 10, then 3s2, 3px2, 3py2 and 3pz1. In beryllium chloride, there are 2 chlorine atoms. It is a single electron present in 3pz orbital that bond with the beryllium central atom. When chlorine atom approaches beryllium, beryllium atom gets excited. That is, its energy level increases. In the previous video, we have seen that there is no need for promotion of electrons before hybridization. But for the sake of understanding, we will consider that when it gets excited, one of the electrons from the 2s2 orbital gets promoted to the 2p orbital. Then the orbital picture of the excited beryllium atom will look something like this. 1s2 has both the electrons, that is, the electron pair with opposite spin. 2s2 orbital has only one electron now. The other electron is promoted to 2p orbital. I have shown it in 2px orbital or 2px orientation. Let me repeat. One electron from 2s2 gets promoted to 2px. Remember, 2px, 2py and 2pz all are degenerate. They have the same energy. This is ground state. This is excited state. After this, these two orbitals get hybridized. 2s2 and 2p. One of the orbitals of 2p get hybridized. And what happens? Two hybrid orbitals are formed. I have shown the bond formation here. We have already seen that unlike the unhybridized p orbital which has two equal lobes, the hybridized orbital has two unequal lobes, one lobe big and one lobe small. I have shown one hybrid orbital of beryllium in blue color and the other in yellow color so that you understand the hybrid orbital. See, the p orbital of chlorine is shown in white color and the two lobes are equal. The two hybrid orbitals of beryllium are aligned in the axial position. Each of these hybrid orbitals of beryllium overlap the unhybridized 3pz orbital of chlorine atom on both sides, which is shown here in this diagram. So this bonding and this bonding, this is the beryllium atom. Let me show it down here. Beryllium bonds with the two chlorine atoms like this. Single bonds. So here the overlapping is axial and axial overlapping gives rise to sigma bond. So beryllium forms sigma bond with the two chlorine atoms separately. The angle between the two bonds is 180 degrees. So the molecule is linear in shape. So hybridization helps to understand the shape or geometry of the molecule. Before we conclude the video, let me explain one more thing. If we try to explain the bond formation in beryllium chloride without hybridization, that is, one of the electron from the 2s2 orbital gets promoted to the 2px orbital. It does not undergo hybridization. Then it directly takes part in bond formation means one bond of beryllium with chlorine will be with the 2s orbital and the other bond will be with 2px orbital. Then the energy level of the two bonds will be different and the shape or the angle between the bonds cannot be explained. The two bonds will be different then. But as we use hybridization concept here, the two orbitals become degenerate. Their energy level is the same and the bond formed also will be the same. After hybridization, each orbital will have only one electron. It pairs with the single electron in the pz orbital of chlorine atom. That is how the bond is formed. I hope the video was of great use to you. If you think it is useful, do like the video, share the video with your friends and also leave your feedbacks as comments. If you have not yet subscribed my channel, do subscribe it now and support me. Thank you very much. We will meet in the next video with another important example of sp hybridization. Till then, bye.